Thank you, and thanks to the organizers for letting me give my talk here. This work that I'm going to present here was done together with my PhD advisor, Nihat Ai, and it is available as a preprint on arXiv. In this work, we're developing a theoretical framework, and I'm first going to describe this framework and then going to show a few results that we got by applying that framework to simulated agents. So this work is about how morphological computation shapes integrated information in embodied agents. So first, let's look at an embodied agent. An embodied agent typically has some kind of sensory sensors here receiving information from the environment, and computational architecture here, a control architecture that processes that information, and a body interacting with the environment. This body can be more or less well adapted to the environment, which leads to the concept of morphological computation. And by morphological computation, I mean the reduction of computational complexity for the controller resulting from the interaction between the body and the world. There are different ways in which the body can interact with the environment, and therefore there are different types of morphological computation measures and variations, and some of which are discussed here in the first two references. So this is a view from the outside, the interaction with the environment. So when we'll go to the inside, to the control architecture, we're going to use tools from integrated information theory to analyze what's going on there. Integrated information theory, as most of you will know, was developed mainly by Giulio Tononi as a measure of consciousness. And in his words, in short, integrated information captures the information generated by causal interactions in the whole over and above the information generated by the parts. This theory went through various phases of development. I've put here as an example only 3 of the many publications in this field, and therefore there exist different branches of integrated information measures. The measure that I'm going to use here is an information geometric one, and the reasoning behind this measure was introduced and discussed in our publication, Complexity as Causal Information Integration. So now we have these two perspectives, morphological computation on the outside and integrated information on the inside, but these two are still part of the same system of the embodied agents, and therefore it makes sense to look at them in a unified framework and to assume that both of these concepts influence each other. And therefore, our hypothesis is that the more the agent can rely on the interaction of its body with the environment to solve a task, so the more morphological computation we have, the less integrated information in the brain is required. In order to analyze this further, we will first formalize our setting here. We do that by looking at the sensory motor loop. The sensory motor loop was discussed, for example, in these 3 references here. So you have the world, and the sensors receive information from the world. They can send information as a direct stimuli response to the actuators, or they can send information to the controller. This controller processes the information, sends commands to the actuators, which in turn influence the environment. Now we can take these interactions here, and if we unfold this in time and assume discrete time steps, then we get to a graphical representation like this here on the right. So here we have the world W, the sensors S, the actuators A, and the controller nodes C. From the information flowing through the world here, not a large part is not relevant to the agent. And since we're interested in the part that's relevant for the agents, we are going to marginalize over the world here. And as an additional simplifying assumption, we are also going to marginalize to one time step and assume that the process describing this is Markovian. So this leads us to this graphical representation here on the left with the joint distribution, which can be described here on the right by these probability distributions. So we have the sensory, actor, and controller states in the time step t that are connected by an undirected edge, so are represented by a joint distribution because of the path that we marginalized over. Then we have the next sensory state given the last sensory and the last actuator state, the next controller state given the last sensory and the last controller state, and the next actuator state given the last sensory and the last controller state. So now we have a system a system in which we can look at how the different parts influence each other and how the information flows here. So we need a measure for the information flow. And I'm going to describe that in general, but we can especially define morphological computation and integrated information measures in this way. So if we want, for example, to measure this connection between the controller here and the actuator, then we first define a set M of probability distributions corresponding to a split system. By that, I mean of probability distributions factoring according to this graph without this connection, so in which the next actuator state is independent of the last controller state given the last sensory state. Then we define the measure by minimizing the KL divergence between M and the full distribution to quantify the strength of this connection. In all of the measures that I'm going to present, this minimization leads to a closed form solution of the sum of conditional mutual information terms. The conditional mutual information between the random variables Z1 and Z2 given Z3 is defined in this way here. So we sum over that and take the logarithm of Z1 given Z2, Z3 divided by Z1 given Z3. Meaning that if this term is 0, then that 2 has really no influence on that 1 given that 3. So now this is a way in which we define some measures. So now I'm going to present the toy example or experiments that we did. We can think of the robots or agents as behaving something like this here on the left. So we have 2 wheels. These wheels can either spin fast or slow. So we have 4 movements: fast forward, slow forward, left or right. And they are not able to stop. And these agents actually look like this. So our simulated agent, this here is one of them. These black lines here are the sensors. They are binary sensors. When they detect a wall, they turn green. Otherwise, they are black. And the blue part here is the body. If the body touches a wall, it turns red. And now we can vary the length of the sensors from very small to very long. And by varying the sense of the sensors, we directly impact how well the agents perceive their environment and therefore how complex the task of moving in that environment is for them. Therefore, this impacts how much computation has to be done by the controller, and it is a type of morphological computation. It has been called pre-processing or morphology facilitating perception. So now the task that our agents really have to do is to survive 2 movements. So we let them move 2 times, and after these 2 steps, we evaluate a goal variable, and the goal is to be alive, so not to have touched a wall. We don't do that by using a machine learning algorithm, but we use a method planning as inference proposed by Atiyah in 2003, and there we treat the actuator and the controller nodes here as hidden variables and optimize the likelihood of success, so the likelihood of being alive after 2 time steps, by using an EM algorithm. I'm not going to present the EM algorithm here, but it is described in further detail, or this method is described in further detail in our preprint. So let's get to the results. These are the actual measures that we use. So morphological computation, again, is the perspective from the outside. So here we measure the information that's relevant from the agent that's flowing through the environment. And on the other side, we have integrated information where we measure how much information is integrated across different points in time, across different types of nodes. So here in our example, the agents only have two controller nodes. Therefore, these are the dashed connections here. So the measure for morphological computation was defined in the first two references here, and there the author also compared this measure with other morphological computation measures and comes to the conclusion that this formulation has advantages over the alternatives. And the second one, the integrated information measure, is our measure here defined in complexity as causal information integration. So as a result, when increasing the sensor length, we see that morphological computation increases monotonically and integrated information decreases monotonically. Thereby, we verify our hypothesis that there exists an antagonistic relationship between morphological computation and integrated information. Now, if we would only look at these graphs here, we would think that, we could think that integrated information is very relevant for the agent in the beginning here because it's very high, but this is not the case. If we additionally look at two further measures, the first one is sensory information, the information flowing from the sensors to the controller, and the second one is control, the command sent from the controller to the actuator nodes. We see this behavior. So at the beginning, when integrated information is high, the sensory information is not that relevant, and also the control is very close to zero, meaning that the controller has next to no influence on the actuator and therefore next to no influence on the behavior of the agent. So therefore, the antagonistic relationship between integrated information and morphological computation can also be observed even in cases in which the controller has no influence on the behavior of the agent. And therefore, it's important of the importance of integrated information in the controller for the behavior of an embodied agent depends additionally on the information flowing to and from the controller here. So these are only a few of our results. We've evaluated more of these measures, so for the remaining connections here, and also we've done further experiments that substantiate these results. But still, these measures are very simplified. So what we want to do is to analyze more complex agents, and by that I mean agents with a more complex morphology as well as a more interesting control architecture and more interesting tasks. And we want to observe these measures during learning because we've seen that an agent can do very well without involvement of the controller when they already learned a task, but we would think that there's a necessary amount of integrated information during the learning. So we're approaching these questions in a collaboration together with the group of Verena Hafner, especially with Yasmin Kim Georgi, by looking at a simulated Pepper robot here. And this work is funded by the DFG as part of the priority program, The Active Self. Thank you for your attention.